you very much for inviting me to give a talk at Cosmos. Over the past few years, I've heard so many wonderful things about this program. So from my students and colleagues. So it's truly an honor to be here and to share my work with you today. So in this presentation, I'd like to explore collective intelligence and herd behavior from a psychological point of view. Okay, sorry. Let me introduce that's okay. What's that?
Oh, sorry. Yeah, but it's some. Oh no. Okay. Okay. Sorry.
Okay. Let me introduce my background. I'm an experimental social scientist with a background in psychology, currently at Meiji Gakuin University. And my recent research focuses on two main themes. The first one is collective intelligence beyond wisdom of crowds in group decision-making. And the second one is the emergence of social norms in groups and their neurocognitive and ecological underpinnings. And in this presentation, I focus on the first theme. And I'll show how two seemingly contrasting social phenomena, namely herd behavior and collective intelligence, are actually two sides of the same coin. And I hope to encourage more user-inspired research on collective intelligence. Okay, here's some background and motivation. Group decision-making is at the heart of any democratic society, and we expect it to produce collective intelligence. But how should we decide together? And how do we actually decide together? And these questions have been central to social sciences for decades. Yet, recent political turmoil, such as the attack on United States Capitol in 2021, which is a drastic example of herd behavior, has shaken our our confidence in the strengths of traditional democracy. And now we are in the era of big data, and some scholars even suggest a shift toward data democracy, that is, by using countless digital footprints that people leave behind, often unconsciously, they argue, these guys, we might achieve better collective decisions than through traditional consensus building. Although this argument may sound rather radical or even outrageous, it might have some parallels with group decision-making by non-human animals. Okay, let's think about the robustness of group decision-making and even data democracy. Like Watal mentioned, collective decision-making isn't just a human thing. We see it all across the animal kingdom. Take social insects, such as honeybees, ants, and so on. They make quite impressive collective decisions, choosing a new nest site or coordinating social foraging. And they do this even though each individual insect has very limited cognitive capacity. They have no human-like language at all. So this is what we call swarm intelligence. And it's not limited to insects. Think of Tonkian macaques navigating as a group, or sticklebacks schooling together, or wild dogs coordinating their hunts. So all these cases seem to point to one thing, that is the adaptive ecological rationality of group decision-making. So the big question is, what algorithms can sustain this robustness across humans and animals alike? So here's an overview of my talk for the next 15 minutes or so. First, I'll define what we mean by herd behavior in the behavioral sciences. Then I'll review several real-world examples to show the herding is both robust and fundamental in human societies. Next, I briefly explain the psychological and neural mechanisms that underlie herding. And after that, I'll move on to related group phenomena, the wisdom of crowds and collective intelligence. Unlike herding, these ideas give us a very different, more intelligent image of collective behavior. But my argument today is that herding and collective intelligence are not separate things. They are kind of twins governed by the same underlying psychological and behavioral principles. Okay. So what is herd behavior? We define it as the alignment of thoughts or behaviors among individuals in a group driven by local interactions rather than centralized coordination. So what looks like central coordination is actually an emergent property of those local interactions. In other words, the macro pattern we call herding emerges from the bottom up, from local interactions among agents without any central control system. So it's easy to think of examples of herding in everyday life. Mass hysteria, mobs, panics, urban regions, bubbles, corruptions, and the animal spirits that drive the economy. So we see these all around us. Now, I'd like to move on to other phenomena, which are less obvious, but highly relevant to the idea of herding. A first example comes from epidemiology, the famous Birmingham herd study, as you know. And this is a long-term longitudinal study. They collected detailed panel data over decades and conducted a social network analysis on body mass index. So here's a demographic, here's a graphic representation of their results. Each node is a person, and yellow nodes are obese people, BMI with BMI greater than 30. And green nodes are non-obese people. And the lines collecting them represent social ties, like family, friendships, business, neighborhood, and so on. As you can see, there are clear clusters, as shown in circles, in the network. Obese people are mutually connected through social ties. But here's a crucial point. Network analysis suggests these clusters are not just due to people choosing similar friends. They emerge from the spread of overeating through social connections. In other words, obesity spreads through social networks in a way analogous to a contagious disease. A second example comes from urban crimes. Here we have an analysis of crime rates by economists. As you see in this quote, crime rates vary dramatically across time and space. Of course, economic and other social conditions also vary, and we'd expect those variations to influence crime rates. But these researchers found that economic and socio-ecological factors explain less than 30% of the variation. Instead, social influence plays a key role. And one person's decision to commit a crime makes it more likely that their neighbors will also commit a crime. And this kind of ripple effect produces dynamic differences we see at the macro level. So in other words, crimes are contagious too. Then why does herding occur? What are neural and psychological mechanisms lie behind it? Here I'd like to sketch some of these mechanisms. The first mechanism is automatic mimicry. It seems to ape is human nature. Okay? So mirror neurons, as you know, are partly responsible for this. As you know, in monkeys, for example, these neurons fire not only when the monkey reaches for food itself, but also when it sees a human researcher, human experimenter reaching for food. In other words, the neuron mirrors the behavior of the other as though the observer itself were acting. And similar systems appear to exist in human brains as well. And this system can produce a reflex-like mimicry. In the top picture here, you can see a newborn macaque imitating the facial expression of a human experimenter like this. Okay. And here's another demonstration. Subjects, this person, watched facial expressions on a monitor. We video recorded their facial expressions at the same time. Okay, let me show you what happened. Okay. So this kind of facial mimicry happens not only for smiling faces, but also for sad faces, fearful faces, angry faces, and it happens very quickly, within less than 500 milliseconds from the onset of the stimulus, okay? And automatic mimicry goes beyond faces. It also extends to body posture, voice pitch, and more. So 2AP is, again, fundamentally human nature. A second mechanism for herding is more deliberate. It involves conscious processing, okay? We humans are quite unique species. We develop social norms, mutual expectations, shared stories, and narratives. So think back to the obesity example. You may decide to eat more because it seems more appropriate given other people's eating behavior. And your action then encourages others to eat more for the same reason. So a self-reinforcing spiral begins. So this kind of spiral has been well studied by social psychologists like Solomon Asch and Muzaffar Sharif, as you might remember from introductory psychology classes. And conformity pressure also shows up in classic stories, like in the Emperor's New Clothes. Given everybody else's silence, it's safer not to deviate. And a bank run is another example of this action spiral. So in short, conforming to others often constitutes a Nash equilibrium in the game theoretic sense. A third mechanism is more rational, what we might call Bayesian conformity. Under uncertainty, it can actually be rational to conform to the public opinion, public judgments of others, while setting aside your own private information. The economists call this process as an information cascade. And in a sequential decision setting, a later actor can rationally follow the choices of those who came before, even if their own private information data points in a different direction. So as an individual level, this is perfectly Bayesian rational. However, as a collective level, it could produce something close to collective madness. Okay, so far, we've been seeing several neural and psychological mechanisms behind herding, ranging from unconscious automatic mimicry to more deliberate rational conformity. These mechanisms are robust and fundamental in our social behavior. But an important question arises: is group behavior always that bad? This question becomes especially relevant when we consider a completely different image of group phenomena, the wisdom of crowds and collective intelligence. So while herding often refers to defective social processes leading to suboptimal group performance, the wisdom of crowds suggests a highly intelligent process, one that can achieve collective wisdom. So how can we reconcile these two contrasting images? In the next section, I'll argue that the key lies in understanding the computational algorithms that guide behavior, that guide individual decision-making and behavior in social settings. Okay, to illustrate this point, I'd like to compare a group performance between two very distant species, honeybees and humans, just like what I mentioned 10 minutes ago. Let's start with group decision-making by honeybees. Tom Seeley at Cornell University has been a leading researcher in this field. So as you know, honeybees live in colonies of more than 30,000 individuals. In late spring and early summer, these colonies sometimes split to avoid overcrowding. Okay? And the queen leaves with about 2/3 of the worker bees, while a daughter queen stays behind with the rest. And here's a critical question. How does a swarm that has left the colony find a new home? In the harsh condition of nature, finding a good home is literally a matter of life and death for honeybees. Okay? So Seeley found that honeybees form a kind of search committee composed of several hundred scout bees. And these scouts fly out to inspect potential nest sites. When they return to the nest, they perform what's called waggle dances to advertise the good sites they found. And the duration of the dance reflects the bees' perception of quality. The better the site, the longer the dance. And other bees who haven't flown out are more likely to visit the sites advertised by the scouts. As a result, high-quality sites receive more advertisement and affect more scout bees. As you can see, this process eventually leads to a group consensus through a positive feedback loop. And here's the most striking finding. Even when different possible nest sites vary in quality, the bees are still able to choose the best site. So the honeybee's performance is quite impressive. But theoretically, a puzzle remains. How do the bees actually manage the problem of interdependency? Remember, the bees communicate their findings through waggle dances. Bees that haven't yet flown out decide where to go by observing the dances of their predecessors. And as you see, this could create sequential interdependencies or autocorrelated errors between decision makers. So carryover and amplification of initial, sorry. Where? Yeah, here, sorry. So carryover and amplification of initial errors could cause erroneous information cascades. So List and colleagues address this puzzle theoretically with a computer simulation model. Let me here explain it briefly. This model assumes two things. First, scout bees are interdependent. They give more attention to nest sites, strongly advertised by others. So they conform to others when deciding where to search. So this is a familiar conformity mechanism. But second, the model assumes that the bees are independent when evaluating quality. Sorry, this doesn't work. なんでこれさ、これが動かないんだろう。カーサーがどっかに行っちゃってる。
それがメイン画面に。
来た。で、下、使えるのか。さっき。But second, the model assumes that the bees are independent when evaluating quality. So the duration of the dance, which reflects the bee's preferences for site, is determined solely by her own perception of the site's quality, not by the waggle dances of the preceding others. So the simulation results show something quite striking. When the right mix of interdependence and interdependency exists, group decision-making works extremely well, even in situations where information cascades could otherwise occur. Now, let me turn to human cases. How do human groups perform in a similar environments? Sociologist Salganik and colleagues published a fascinating paper in Science in 2006. The macro phenomenon behind their work is familiar. Hit songs, best-selling books, blockbuster movies, these are many times more successful than the average. So this pattern suggests that the best products qualitatively different from the rest. Yet, experts routinely fail to predict which ones will succeed. So the key question is this: why do inequality in sales and the unpredictability of sales success occur? To address this, they conducted a large web experiment. They created an artificial music market with over 14,000 young participants recruited from a teen interest website. And on this site, participants saw a list of previously unknown songs from unknown bands. So they chose which songs to listen to, rated them on a five-point scale, and they then could download the song if they wished. Okay, this picture on the right here shows the setup of the music market experiment. And there are two conditions. In the independent condition, participants evaluated songs individually. So this is a solo condition, okay? And with no information about other people's choices. In the social influence condition, participants could also see how many times each song had been downloaded, okay, by previous participants. So they were informed about other people's behavior choices. Okay, first let me show you the results about sales volume. These graphs show inequality in download counts between songs. There are 8 different rounds in the social influence condition, and the y-axis represents inequality in download counts between songs measured by Gini coefficients. As you can see here, inequality in sales was much higher in the social influence condition compared to the independent solo condition. Participants in the social influence condition obviously copied the choice of the predecessors, and this produced a kind of winners take all outcome at a group level. In other words, the experiment successfully replicated a robust phenomenon in cultural markets, that is the superstar phenomenon, where hit songs are many times more successful than average. Now, here is theoretically more important question. Did the success of a song in the social influence condition actually reflect its quality? Of course, song preferences are largely a matter of taste without any objective benchmark. But we might assume that a song endorsed by many independent individuals is in some sense of higher quality. So here are scatter plots comparing sales shares of the same songs in the independent condition and the social influence condition. And each dot represents a song. The x-axis shows popularity in the independent condition, and the y-axis shows market success in the social influence condition. As you can see here, there's a positive correlation. Songs popular among independent listeners tended to do well in the market. But there's also a lot of variability, especially in experiment 2. The best song is the independent condition, this end, never do terribly in the market, whereas the worst songs never become runaway hits. But almost anything else is possible in the middle range around here. In other words, success in the music market does not necessarily reflect a song's quality. And this may be one reason why it's so difficult, even for experts, to predict which products will succeed. So, did humans outperform honeybees? I'm afraid the answer is no. Then what explains the difference? As you might recall, honeybees combined independence and interdependence remarkably well in their nest searches. They were influenced by other bees' choices about where to go, where to search, but they evaluated the quality of nest sites independently and formed their preferences on their own. In contrast, humans in the music market failed to keep these two phases of decision making separate. So they relied too heavily on other choices, and this difference produced a substantial performance gap at the collective level between the two species. Okay, as a small side note, we recently conducted an evolutionary game theoretic modeling study comparing two distinct algorithms. A paper based on this modeling is currently under revise and resubmit at PNAS, and we are hopeful it will be accepted soon. Okay. Okay, let me give you an interim summary of what we've seen so far. Evidence from behavior science suggests that our basic social mechanisms, from automatic mimicry to rational conformity, are deeply rooted. These mechanisms are likely evolutionary products that helped our ancestors survive in challenging environments. However, these once adaptive tools can sometimes create serious errors in modern environments where the interconnectivity between individuals and the externalities of their behaviors are far denser and larger. So this is one important take-home message I hope will be useful for social engineers. And another message I'd like to propose is this. Herding and the rhythm of crowds are twins, regulated by the same basic adaptive tools. So given this, I strongly believe that understanding the neural, psychological, and behavioral mechanisms that can help dissociate these twins is one of the most important challenges in behavioral sciences. Okay. Now, let me move on to collective intelligence beyond the wisdom of crowds. Recently, we wrote a review article on this topic. For the rest of my talk, I'd like to highlight some of the key arguments from that paper and show you several computational and social algorithms that can yield collective intelligence above and beyond the wisdom of crowds in teams, in group collaborations, and beyond. Okay, let's start with the wisdom of crowds phenomenon as a benchmark. As you know, the most famous example was provided by Francis Galton. And as you know, at the country fair in Plymouth in 1906, there was a contest to estimate the weight of an ox. About 800 people participated. And Galton observed that the simple average of these ordinary people's judgments was remarkably accurate, outperforming any single expert. Although Galton's demonstration was quite impressive, it's important to remember that this is a purely statistical phenomenon. Okay? Individual random errors are filtered out by treating everybody's input equally in group aggregation. So this cancellation of individual noise also underlies majority or plurality aggregation, plurality voting in consensus decisions, and the copies a majority algorithms in combined decisions, as shown by the Condorcet-Jury theorem. So not surprisingly, these simple statistical aggregation processes are also widely observed in non-human animals as well. This suggests that majority and plurality aggregation are generally adaptive under uncertainty, effectively solving the speed-accuracy trade-off in group decisions. Now, to think about collective intelligence beyond the wisdom of crowds systematically, we first need to distinguish between two types of group decision-making. The first is consensus decision-making. Here, members make decisions together with reaching a consensus as a common goal, like Congress or jury. Okay? The second is combined decision-making. Here, members make decisions individually, but they are influenced by other group members. For example, in consumer choices or public goods provision. Okay? And in such combined decision-making, individuals do not necessarily aim to coordinate or cooperate to make good decisions as a collect group level. So this can lead to suboptimal macro outcomes through individuals' egocentric or myopic behavior, and of course through herding. Okay, here's a summary table of various information pooling mechanisms in consensus decision-making, this side, and in combined decision-making. And these aggregation mechanisms can be arranged according to how information inputs are distributed among members. For example, in consensus decisions, mechanisms like unanimity or majority law assume that each member contributes equally. And in combined decisions, mechanisms like random copying or copy the majority also assume equal information input from all members. On the other hand, some mechanisms are based on skewed information inputs from just a subset of group members. In consensus decisions, that would be accuracy or expertise-weighted aggregation, or even despotism, dictatorship. And in combined decisions, that would be advice taking or prestige bias copying. Then, can we think of other aggregation methods that can produce even better collective outcomes above and beyond the wisdom of crowds? So rather than giving equal weight to everybody, it seems not natural to weight each person according to their expertise, their knowledge, their ability, and so on. And this could yield better collective performance than simple error cancellation that underlies the wisdom of crowds. In fact, decision scientists have proposed various aggregation methods to capitalize on individual heterogeneity in expertise. For example, weighting each person's input by their past performance, their judgment coherence, or the similarity of their decisions to others. But as you can see, there's one major drawback. To assess individual expertise accurately, we need longitudinal and thorough observation. And there's another issue. If optimal weighting schemes are tuned too sensitively to finite or noisy data, they may fail to outperform equal weighting when applied to new data sets, which is known as a classic bias variance trade-off. Okay? So while statistical aggregation weighted by expertise can be useful, its applicability might be limited to specific cases. Okay, so far I've been talking about statistical aggregation imposed from kind of the outside, that is some outside observer or outside system judges people's expertise and aggregates their judgments into a group decision, okay? But rather than relying on an outside system, we often infer each other's expertise through social interaction when we make group decisions. In these cases, subjective confidence may play a critical role. In cognitive science, subjective confidence is regarded as a metacognition, our own sense of how much we know and how accurate we are. And importantly, subjective confidence can be communicated by verbal or physical cues such as tone of voice, posture, and so on. So expressed confidence might serve as a useful proxy or for expertise to guide consensus. This idea has been elaborated by Valami and others. Let me explain their study briefly. They set up an experiment where two people must reach a consensus through discussion. So for illustration, imagine two judges in a tennis match. They disagree about whether the ball crossed the sideline. One guy says, I clearly saw the ball landed out. And the other guy says, it seemed in, okay? As you hear, Judge A sounds more confident than Judge B. But in actuality, Judge A's reliability in terms of sigma here is worse than Judge B's. And from a composite statement such as, I clearly saw the ball landed out, it's impossible to differentiate between the strengths of the perceptual experience and the perceptual reliability behind it. So from these composite statements, composite confidence statements, optimal aggregation of the two judgments according to the signal detection model becomes impossible. Indeed, the experimental results showed that peer discussion can be approximated by a confidence-weighted aggregation by an aggregation model, which is Bayesian optimal. But it fails to achieve the very best possible group level accuracy. So the question is, can we overcome such a limit of expressed confidence in verbal statements? Our conjecture is yes. And here's our claim, main claim in the review paper. Behavior opt-in or opt-out mechanisms may be the key. That is, consensus decision-making usually emphasizes or even idealizes that all members contribute equally. Equal participation of all is a nice principle. But a more realistic scenario may be this. Members' behavior opt-in or opt-out of the decision-making process according to their relative expertise. More confident members, possibly with accurate metacognition about their high expertise, are more likely to contribute, whereas less confident members may refrain from contributing their judgments to the group discussion. Of course, the success of such opt-in, opt-out mechanisms critically hinges on one key question. To what extent is subject confidence a reliable metacognition about one's own expertise, as we saw in the Bar-Lamy case? But here's our point. The linkage between expertise and participation itself may actually evolve through social interaction. Okay, let me explain. I'll show you some basic evidence that the opt-in, opt-out mechanisms can improve crowd judgments. For instance, Bennett and colleagues ran a very simple experiment. Participants answered several general knowledge quizzes like, what's the population of Chicago in 2022? And there are two conditions. In one condition, quizzes were randomly assigned to each participant. And in the other, participants were allowed to choose which quiz to answer. Although this setup looks quite simple, the results were illuminating. Volunteered opt-in judgments were more accurate than forced randomly assigned judgments. And also, good respondents tended to answer more quizzes than bad respondents. So allowing respondents to opt-in or opt-out can build a more informed knowledge base for group consensus. Although anecdotal, let me show you an impressive real-world example. Barbara Mellers and her colleagues joined the US government forecasting tournaments, aiming to develop new methods for predicting high-impact events worldwide. And in their winning approach, forecasters were teamed up and interacted on a website. This was the team condition, okay? And compared to the crowd belief condition, where people only saw the distribution of others' forecasts without interaction, the interactive team condition yielded superior collective performance. And most strikingly, super forecaster teams composed of top 2% people from the first year outperformed all the other teams by a wide margin for 2 years in a row. So what was the secret of their outstanding performance? Turns out members of the super forecaster teams provided information quite selectively, only on questions they were firmly confident about. Other members who stayed silent but had high general abilities judged the quality of the evidence proposed. So this produced a kind of high-level cognitive division of labor, guiding who should contribute, who should listen, and when. And most importantly, all this emerged through social interaction. But you may be thinking, isn't this just a champion case? And doesn't it only apply to super special teams of highly motivated experts. Okay, that's a fair question. So now let me pivot to a more general principle. The copy when uncertain strategy in combined decision making. This is one of the most established social learning strategies found across humans and non-human animals. A mechanism for when each agent decides individually, okay, without trying to reach consensus, but still knowing how others behave in the same environment. Okay, here I'd like to explain the copy when uncertain strategy. This is a social learning strategy about when individuals should copy others. If you don't have reliable information about a new environment, it's usually better to copy others. But if you do have the relevant knowledge, you can act on your own. As a result, copied behaviors originate from well-informed individuals in a group. So less informed individuals tend to wait and observe before acting. So this conditional use of social information is actually driven by pure self-interest as an individual level. But here's an important point. Even though it's individually motivated, this dynamic improves the quality of the information pooled within the group. In other words, it works very much like the confidence-guided opt-in, opt-out mechanisms that will be seen in consensus decision-making. There's some evidence for this claim. Several years ago, we conducted information cascade experiments in Japan and in France. In the experiment, 30 participants answered knowledge questions like in a sequence. For a given question like, what is the radius of the fan? Each participant first gave her personal estimate. Then, after seeing social information, which was a moving average of the 3 preceding members' estimates, she gave her new estimate. So this process was repeated across 30 people in the chain. You immediately notice that this setup could easily lead to erroneous information cascades via autocorrelated errors spreading down the chain. So this experiment setup provided a very challenging situation for collective intelligence to emerge. However, the results showed that social information did improve collective performance. This graph shows average performance in the first solo estimates in blue and the second estimates after receiving social information in red. The x-axis refers to various experimental conditions, and the y-axis means accuracy. And here, the smaller the number, the more accurate the estimate. As you can see here, the second estimates in red were more accurate than the first solo estimates in blue. So, despite the possibility of autocorrelated errors in the chain, collective intelligence did emerge via social information. Notably, this pattern was observed both in Japan and in France, 2 countries that are often contrasted culturally in terms of conforming Japan versus independent France. Okay, so what's the mechanics for? What are the mechanics for this? This graph shows the relation between individual confidence and accuracy. As you see, more confident participants toward this end are also more accurate. Now, the right graph shows the relation between confidence and independence. As you see here, more confident participants are less susceptible to social information. So these 2 behavioral elements, higher accuracy with confidence and greater independence with confidence, together form the copy when uncertain strategy as a package. And this package contributed to collective intelligence even in a chain where erroneous information cascades could otherwise occur. Okay, let me wrap up the second part. In this part of my talk, I have argued that opt-in, opt-out process may be one of the key mechanisms for collective intelligence above and beyond the collective wisdom of crowds. I've shown that higher order metacognitive division of labor, capitalizing on individual differences in knowledge and accuracy, could emerge through social interaction. And prototypes of such division may also be behaviorally manifested in group living animals. Furthermore, I'd like to emphasize that copy when uncertain strategy, which is functionally equivalent to the opt-in, opt-out process in consensus decision-making, is widely observed in combined decision-making by both human and non-human animals. And such metacognitive division of labor can develop as an emergent property in micro to meso-sized groups where relatively fixed members repeat interaction over time. On the other hand, it is quite a challenging issue whether and how such coordination is viable in macro-sized groups, as we often experience in the internet community. Perhaps introducing some kind of human-machine ensemble might help create and sustain useful coordination in such macro-sized groups. But because this is not within my area of expertise, I think I should opt out here. And here's final conclusion. Today I have presented an adaptation-based meta-theoretical perspective for understanding collective behavior. The adaptive tools we acquired through biological evolution can sometimes cause serious errors in modern societies where the interconnectedness of individuals and behavior externalities is much denser and larger. Second, I've emphasized that herd behavior, which is Hyde, and collective interest, which is Jekyll, are not different phenomena, but rather inextricably linked, controlled by the same basic mechanisms. I hope that this perspective will help guide user-inspired research addressing specific problems related to collective intelligence. And finally, I believe this meta-theoretical approach can complement bottom-up brute force big data approaches by helping us identify in advance those key parameters that are more central to the focal problem and should be fine-tuned or measured more precisely. Okay, thank you very much for your attention.